The focus of this second lecture will be on the S process. Now, in the first lecture, we looked into the evolution and nucleosynthesis of low and intermediate mass stars. So these are stars with masses between about 0.8 to 8 solar masses. And we looked at their evolution at various phases from the main sequence through to core helium burning and then onto the asymptotic giant branch, which is where the S process can occur. Here we're going to take a step back and we're first going to introduce you to the S process, focusing on how it occurs and what sort of expectations we have about the production of elements from the S process. There we will look at sites of S process element production. The majority of our focus here will be on the theoretical models of Agb stars, but I will briefly mention the S process in massive stars. I will also, I guess the last couple of sections, so the next section will be discussing a couple of puzzles and the intermediate neutron capture process, which may also occur in the same site as the S process, but under different neutron density conditions. And the final section will be on the chemical evolution of heavy elements. So this is how, this is the how heavy elements change with time in the galaxy, essentially. All right, but let's start with a broad introduction. So by heavy elements here, we are really focusing on elements heavier than iron. Here, the number of protons in the nucleus is so large that electrostatic repulsion inhibits fusion reactions. And by fusion, I mean charged particle reactions such as alpha or proton capture. Most of our heavy nuclei are formed by neutron addition onto iron peak elements. Now, there are exceptions, but for the, I'm not going to, what will not focus on those at all, but just focus on the main way that heavy elements are made. Now, two processes were identified in nature. These are the rapid neutron capture process, and there will be other lectures on the R process, and also the S process. And between these two processes, we think they make roughly half of the elements heavier than iron each. So my focus will be here on the slow neutron capture process. I've put a couple of references about both processes, but I'm sure the lectures on the R process will provide you with more about those. Okay, so this is a periodic table showing the origin of elements, and I really like this. This was made for a press release, but again, we're focusing on elements heavier than iron, and you can see from this, so this is from Z of 26. So if we look at this periodic table, we see that this is indeed almost the majority of elements in this table. So charged particle reactions in massive stars and low mass stars make elements up to iron. Explosions in supernovae make the iron peak. But really for elements above iron, which is, as you can see, it's a huge number of elements in this table, everything from essentially really zinc and copper, all the way up to uranium. Most of these elements, the majority are made through neutron capture processes. This is color-coded. This is color-coded by a number of different ways. You may have seen versions of this table, but here we're color-coding by, so if you like, there's a little time bar on the x-axis of each of these elements. And what we're showing here is color-coded by how much of that element is made by different processes. If you focus on lanthanum, Z of 57, you see that the majority is produced by dying low mass stars. These will be the Agb stars we focused on previously. Whereas if you focus on another element such as iodine, Z of 53, we see the majority is made by, here, exploding massive stars, not even merging neutron stars. I'm not going to discuss the R process or its sites, but just to note that there are, of course, likely different sites of the R process, just like with the S process. Okay, so this is just a bit of a taste of the sorts of things that we want to be able to do. So this is a quantitative, I suppose more qualitative view about the chemical evolution of elements as a function of time, given our current understanding. This, of course, these types of plots, of course, may evolve and change as we learn more about, for example, merging neutron stars, exploding massive stars, dying low mass stars. Okay, but this is the introduction. So we've sort of summarized, well, I didn't really summarize too much where the elements come from. You'll have lectures, of course, by Alex Hager, who'll talk about massive stars. This is where the majority of the charged particle reactions from carbon through to calcium come from. Supernovae make iron peak elements through nuclear statistical equilibrium. And then we have neutron captures making elements heavier. Now here, this is a plot showing the solar system abundances as a function of atomic mass on the x-axis. I really like this plot for a number of reasons. So first of all, so the y-axis is the log abundance relative to silicon, which has been scaled to 10 to the 6, and everything else is scaled around that. Now, I really like this plot because we can see distinct peaks at selenium and strontium, at tin, xenon and barium, and platinum and lead. Now, we want to understand where these peaks come from. We also want to understand the general shape of the production of elements heavier than iron. So we want to understand the origin of these solar system abundances. So let's just start at the beginning. So how do neutron captures work? Neutron captures in general are what we call a secondary process. So you need to start with generally a seed nuclei. That seed nuclei is normally iron because there's so much of it. If you look again at the solar system abundances, you see that there's a huge peak in iron, and particularly iron 56 in, for example, solar system abundances. Iron is one of the most dominant elements. So it's a good place to start if we want to bombard something with neutrons and make heavier elements. Iron also has a high neutron capture cross-section, which we'll get to later. So let's start with iron 56. There's a lot of it in stars. You bombard it with neutrons, it makes iron 57. You bombard it with iron 57 with neutrons, you make iron 58. You add another neutron, you make iron 59. Now, iron 59 is a radioactive isotope. It is unstable. It can do one of two things. Iron 59 can capture a neutron itself to make iron 60, or it can beta decay to cobalt 59. So I've shown on the chart of the nuclides down below the choice essentially that iron 59 has. So does it capture a neutron to make iron 60, or does it beta decay to cobalt 59? So it makes a new element because you're converting a neutron into a proton. Now the details, the pathway of iron 59 depends essentially on the neutron density. And this really distinguishes the S process from the R process. The S process is a slow process. This means that the timescale of N gamma reactions is generally much longer, it's much slower than the respective timescale for beta decays. The relative neutron densities of the S process are on the order of 10 to the 8 neutrons per cubic centimetre. What does this mean for the S process? Well, if we take a section of the chart of the nuclides, and this is a real section around zirconium up to ruthenium, or yttrium really up to ruthenium. So again, neutron number increasing on the x-axis, proton number on the y-axis. And I've drawn in with the blue lines the path of the S process. Now you notice that and what the S process does essentially, because it's the timescale for neutron capture is in general much longer than the timescale for beta decay, it meanders up the valley of beta stability. So it'll stay very close to this valley of beta stability. Let's have a look as an example. If you get to zirconium 95, zirconium 95 is an unstable isotope with a half-life of 95 days. Again, it has a choice. Does it capture a neutron or does it decay? And under most conditions of the S process, zirconium 95 always decays. So it decays through niobium 95 up to molybdenum 95, and that's where the process starts up again. And then that's a stable isotope, it starts capturing neutrons until it gets to molybdenum 99 with a half-life of 66 hours. So the rough order of magnitude is unstable isotopes that have half-life shorter than a few days, they will generally decay instead of capturing a neutron. So this keeps us very close to that valley of beta stability. I've highlighted here two isotopes in particular. One of them is zirconium-96. This is in general an R-only isotope. It can be made by the S process under very specific conditions, but generally most of the zirconium-96 in the galaxy is made by the R process. The other isotope I want to highlight is molybdenum-96. Now, imagine we have an R process. So we're not going to, again, worry about details, but imagine you have huge flux of neutrons. You go all the way out. So in this case, the timescale for neutron capture is much shorter than the typical beta decay half-lives. So that means that you're much more likely to capture a neutron. In fact, you don't have time to beta decay. You just capture neutrons. You're all the way out to the neutron drip line. You shut off your source of neutrons and then you decay back. And you decay back in beta decay lines at 45 degrees and you get to zirconium-96. So you decayed all the way back. So you've gone to the unstable isotope with mass number 96 and you decay to zirconium-96. But you stop there. So you can't decay any further because zirconium-96 is stable. That means that molybdenum-96 is what we call an S-only isotope. It is shielded by the R process by zirconium-96. So that means the only way we can make molybdenum-96 is under conditions of the slow neutron capture process. Okay, so sometimes you may hear about S-only and R-only isotopes, and this is where that comes from. There are, of course, branching points. Now, this is the same chart, and here I've color-coded it this time by half-life. So I've taken this from, so there's a website called the Colourful Chart of the Nuclides, and this is by Ed Simpson at the ANU, the Australian National University. And Ed has made this website where you can color-code the chart of the nuclides by all sorts of things. So here I've color-coded by half-life, and I've put in the solid line the path of the main path of the S process. So you see that it goes through the zirconium isotopes, it gets to zirconium-95, and under most conditions in most stars that experience the S process, zirconium-95 decays, and it decays to molybdenum-95. So zirconium-96, which is for all intents and purposes stable. You see, it's actually technically not stable, but it has a half-life much, much, much longer than the age of the universe. So zirconium-95 is in general only reached by the by the R process. So what we have here is that we say that zirconium-95 is a branching point. If you have a high enough neutron density, you can bypass this branching point, and then the probability of neutron capture starts to overrule the probability of beta decay. That turns out to be about maybe 10 to the 10 neutrons per cubic centimetre. So there are some stars that have S process-like conditions that can make zirconium-96. Now, you notice that zirconium-93 is marked as, it's marked more or less as stable here. The S process goes through it as if it was a stable isotope. So that we have a solid line that goes through zirconium-93, there's no branching point at zirconium-93. So however, it has a half-life of 1.6 million years. And so for the purposes of the S process, we consider zirconium-93 to be stable. And that's why, even though it's actually marked as unstable here, it behaves like a stable isotope for the purposes of the S process. And that's what that slide was meant to say. Okay, so in order to understand why we have peaks in the solar system abundance distribution, we have to consider the concept of magic numbers. So quantum mechanics teaches us about the stability of closed electron shells. We have similar things happen in the nucleus. When a complete energy level is filled, it is particularly stable, and it's not just stable. For our purposes, it has a low neutron capture cross-section for reactions. Now, this happens at numbers of 2, 8, 20, 28, 50, 82, and 126. Now, these magic numbers apply to neutron or proton, so either for neutron captures or proton captures. And a nucleus that has a magic number of both neutron number and proton number is said to be doubly magic. Examples of doubly magic isotopes include oxygen-16, nickel-56, and in fact, a lot of nickel-56 is usually made by supernovae explosions. And this, of course, leads to the production of iron-56, and also lead-208. And lead-208 is the endpoint of the S process, unsurprisingly. Okay, so what are the consequences of this? Well, first of all, let's go back to our abundance distribution in the solar system. Again, let's not worry about the peaks less than iron. We have iron peak as a high spinning energy. We have abundance peaks from magic numbers less than iron. So these are less than 20, less than equal to 20. But you also notice that there are peaks at selenium, strontium, tin, xenon, barium, platinum, lead. These are caused by abundance peaks from nuclei with magic numbers greater than equal to 28 in the chart of the nuclei. Barium 138, for example, is most of the barium in the solar system, and this happens to be a nuclei with a magic number of neutrons. And we see similar behavior in all of these peaks. So essentially, these peaks are caused by magic numbers of neutrons for elements heavier than iron. So what do we see if we look at the neutron capture cross sections? This is a fairly old plot, but I really like it. This is from Donald Clayton from his textbook. And we have atomic weight on the x-axis and versus the cross-section, so the neutron capture cross-section in millibarns, where 1 barn is 10 to the minus 28 meters squared. So this sigma, now for those of you who are nuclear physics students, you know what sigma is. If you're not a nuclear physics student, this is the probability essentially of capturing a neutron. So typical neutron capture cross sections for the S process, or typical neutron capture cross sections are measured in the order of millibarns, but they may be as large as 1,000 millibarns or 1 barn, as you can see from this plot. So, but the thing that I really want to highlight here is that we've located, so there's a few points, Z of 28, Z of N of 50, Z of 50, and N of 82, as well as Z of 82 and N of 126. Notice that the cross sections, these sigma cross section at those particular points correspond to magic numbers of neutrons or protons here. They're orders of magnitude lower than neighboring nuclei. What does that mean? Well, let's imagine that this is essentially a cross-sectional area. If you have a large cross-sectional area and you bombard something with neutrons, it's more likely to be captured. But what if I shrink my cross-sectional area? It means that I can bombard it with neutrons, and it's unlikely that neutrons are going to go past it and get captured. So this means that we tend to build up the abundance of isotopes that have a magic number of neutrons. They have a low cross-section. They don't like to capture neutrons, so it's hard to what we call bypass these isotopes. It's easy to build them up, but it's hard to get past them. This is a table that shows isotope number, the number of protons, the atomic mass, the sigma cross-section in millibarns, and the solar system fraction of that isotope. Now, I've taken this data from a whole lot of different places, but one thing I want to highlight is barium. Let's just focus on barium for the purposes of this exercise. So we've got 2 barium isotopes, barium 135 and barium 138. 138 has a magic number of neutrons, so it's got 126. You'll notice that even though they have the same number of protons, their neutron numbers are really different. And if you focus on their sigma cross sections, they're 2 orders of magnitude different. So there's a factor of 100 different in their neutron capture cross sections. Now look at their solar system fractions. You'll see that the amount of barium 138 in the solar system is also an order of magnitude higher. So most of the barium in the solar system is barium 138, almost 72%, whereas only about 6.5%, 6.6% of solar barium is 135 in comparison. So this is where the consequence of nuclear structure play a role in the abundances that we see around us, essentially. All right, so our S process peaks, they correspond to nuclei with neutron magic numbers. So N of 50 82 and 126 because the neutron capture path goes right through them. The R process peaks correspond to unstable nuclei with neutron magic numbers. You decay and then you decay back and you end up to the left of the S process peaks. So you end up at xenon and platinum as opposed to barium and lead. Okay. Now, this is the, again, a path of the, so this is the section of the chart of the nuclides around zirconium to ruthenium. So focusing on this region of the chart of the nuclides. Now, anything strange here? You notice that this element, technetium, has no stable isotopes. The longest lived are technetium 97 and 98 that almost have the same half-lives of about 4.2 million years. Now, the thing is that technetium is observed in stars. We see some stars. They're not on the main sequence. These are evolved red giant stars of fairly low mass, and they're observed to have technetium in their spectra. So they have spectral, so we see absorption lines in the atmospheres of some low mass stars that are red giants that have technetium in them. How? Where did it come from? This is a real hint for nucleosynthesis. It turns out that the stars that that have technetium in their atmospheres are Agb stars. They are stars, they're past core hydrogen and helium burning, and they're on the asymptotic giant branch. So this is a huge hint. Now, which isotope is made by the S process? I put a line through molybdenum up to molybdenum 99. Molybdenum 99 will decay, so it has a reasonably short half-life. Molybdenum 100 is R only, so we decay a molybdenum 99 and we decay to technetium 99. So this is a technetium isotope made by the S process. Now, technetium 99 also has a fairly long half-life of about 200,000 years. So that means if you see technetium in the atmospheres of stars, it must have been made relatively recently. Why is that? Well, the stars that we see observed with enrichments of technetium, so they have technetium in their atmosphere, that's what we call by an enrichment, they must have been made, these stars have lifetimes of billions of years. That's much longer than the technetium half-life, whether we're talking about technetium 99, which may also capture some neutrons to make technetium 100 maybe, but that has a much shorter half-life. So regardless of what technetium isotope we're dealing with, the stars have much longer lifetimes. So we're not talking about stuff the star was born with. It must have made it. And this is a huge hint. So this takes us to the site of the S process. So this is a summary slide. So I'm essentially skipping to the end in some way, but I think it's useful to start essentially at the end. In terms of the rapid neutron capture process, it makes half of the elements heavier than iron. You'll hear a lot more about this, but the broad summary is that 2 sites have been identified, both from theory and maybe even observation. Anyway, I'll leave the discussions you to make up your mind from the discussion you hear. But roughly, neutron star mergers have been confirmed observationally, and then we also think from theory that perhaps magneto-hydrodynamically driven supernovae. In terms of the S process, 2 sites have been identified: asymptotic giant branch stars confirmed by observation and theory, and massive stars during their hydrostatic burning phases. So these are stars more than 12 solar mass. They explode as iron, core collapse supernovae, and the S process we think is made in the carbon and helium burning zones of this star and before the supernova explosion. However, it requires a supernova to expel that S process into the galaxy. However, Agb stars are the main site. Most of the S process elements between, say, strontium and lead are made in Agb stars. Okay, S process in massive stars, I don't want to focus on this, just to give you a slide. Here we're producing heavy elements in the helium and carbon burning shells of these stars. This is mainly what we call the weak S process. You'll often hear weak, main, and strong. Weak refers to S process from copper essentially to strontium. There is a classical reason for these names. If you look at Donald Clayton's textbook, you can learn more about this. Now, the main neutron source, and I will talk more about neutron sources later, about the AG, when we talk about how the S process works in Agb stars. But the main neutron source is neon 22 alpha N. That makes magnesium 25. So here, however, usually the neon abundance scales with metallicity. So if you have a very low metallicity star, you don't have much neon 22, except when there's rapid rotation. Now, I'm not going to go into details, but there's a whole lot of recent papers about rapidly rotating low metallicity massive stars and how they can make S process. And I have a plot from a paper by Choplin and Hershey from 2020. And I encourage you to read these references if you want more details. Okay, but Agb stars are the main site of the S process. And so I mentioned weak, main, and strong. So main means between essentially strontium up to lead, and the strong is just lead. So this was identified through analytical examinations of the S process. Now, the Agb stars make most of the S process elements between strontium and lead, and we know this from observations. Technetium is such an element, and we have many other observational confirmation of this process. Now, this is an example. It's just a public press release slide on the left-hand side showing the rubidium line. So rubidium, of course, is just near strontium, and it can be made by the S process. And in particular, it can be made by Agb stars at the upper end, so by more massive Agb stars. So where is the S process made in these stars? Well, likely in the helium-burning shell, but we will get to that in a few slides. First of all, let me give you some evidence of heavy element production in Agb stars. This plot, we have number of protons on the x-axis. So this is element number versus X to iron. So on the y-axis, this is that square bracket notation. Now recall from that first lecture, 0 means the solar ratio. It's log 10 of the solar ratio. 1 is 10 times more than the solar X to iron ratio. 2 is 100 times more than the solar X to iron ratio. And what we can see in this plot here is that those points with error bars, they are the measurements of heavy elements in a post-Agb star in the Large Magellanic Cloud. For those of you who don't know, the Large Magellanic Cloud is a nearby satellite galaxy of our Milky Way. The good thing about this location, this nearby Large Magellanic Cloud, is that we know the distance to this object. If we know the distance, when I measure the luminosity of my post-Agb star, I can work out what a true luminosity is because I know the distance to this object. Usually in astronomy, distance is really problematic. So I know how far away it is, so I know the location, and I can determine luminosity. Once I know luminosity, I can work backwards and provide an estimate on the star's current mass. So maybe it's core mass, because with Agb stars, these things correlate. So we know roughly what mass the star is that's making it. And I just want to highlight here, if you notice again, let's go back to that 100 times more, that many of the elements from zirconium and heavier are enriched in this post-Agb star almost up to 100 times the solar ratio in some cases. So this star is incredibly enriched in S process elements compared to the solar system. Before I go further, I just want to briefly mention there is often these definitions in the literature that's sometimes worth knowing about. One of them is that often, if you look in the observational literature of S process and Agb stars, you'll come across this intrinsic and extrinsic. What do they mean? It simply means that intrinsic is a star that's self-enriched in S process elements. It is currently on the Agb. It's experiencing thermal pulses and third dredge up, which is what I talked about in the first lecture. And it has spectral types, maybe of N, SC, S, C type. So it's a real Agb star going through its own third dredge ups. Extrinsic, this is a star that obtained its S process elements from another star, perhaps as a result of binary mass transfer. Extrinsic could also be a star that formed out of a pocket of the interstellar medium that was really rich in S process elements. But perhaps in reality, I don't think we found any that actually match that. Maybe. So we have examples of what we call extrinsic S process enriched stars. These are barium stars, CH type stars, and carbon enhanced metal pore stars. So how do we determine whether we have an intrinsic star or an extrinsic star? Well, remember radioactive technetium. If a giant star is enriched in carbon, S process elements and technetium, it must really be on the Agb, making its own heavy elements. If it has all of that, but it doesn't have technetium, there's no evidence it made its own elements. It likely received that as a binary mass transfer gift. So extrinsic stars, what if we find a star that is enriched in S process elements, but there is no technetium? If it's not on the Agb experiencing thermal pulses, then it must have obtained its enrichment elsewhere. In fact, it might even be on the Agb, but it hasn't experienced thermal pulses yet. So the question is, it didn't make those elements itself. Often one thing we want to know, is the star a binary? If it is, then yes, then we can be sure that it obtained its elements through binary mass transfer, especially if the companion is a white dwarf. And with barium stars, they're all binaries, 100% of them, and they all have white dwarf companions. So that's kind of tick, tick, tick. This star received its S process through binary mass transfer. These are known, these barium stars, CH carbon enhanced metal pore stars, CHEMP. These are long period binaries where the originally more massive companion was an Agb star and is now a white dwarf. We see evidence of nuclear process material, such as carbon and barium, on the surface of the present day giant star. So this is the star that received its barium from the star that's now the white dwarf. This is evidenced for mass transfer by what we call stellar wind accretion. So when that white dwarf was on the Agb, it had this thick, dense stellar wind. The companion went through that wind and slowly sucked up a bit of that stuff. And this is shown by a 3D hydro simulation from a group in the Netherlands. Okay, so what question is, we know Agb stars can make S process elements. We have some, from observations, we have some hints at the mass ranges. Observationally, these are low mass stars with initial masses less than about 3 solar masses. However, it's worth pointing out, and I will say it again, that determining mass for stars is difficult. And it was one of the most difficult problems pretty much up until the recent era. That means especially for stars in our galaxy. For stars in other galaxies, if we can see that, if we can resolve individual stars, then it's easier because often we can determine the distance to that galaxy. But for stars in our own, which we have the best observations of, we don't know. Determining how far away they are has been incredibly difficult until the Gaia era. There have been some new papers on looking at the masses of stars with well-determined distances from Gaia, and I recommend you have a look at these. Are papers by Shetty, 2019, 2021. So, but these are still low mass stars, regardless. The stars in the post-Agb stars in the Magellanic Clouds have been really crucial to our understanding of the S process, and also in recent times, because first of all, we've been able to determine high resolution abundance analyses, what sort of elements they have, how they're enriched, but we've also been able to determine their initial masses. This is often with telescopes, such as the very large telescopes based in South America. So again, once we know the distance, we can estimate luminosity, we estimate core mass, and we get the initial mass. We can at least estimate it. And this tells us that most stars that are enriched in S process elements must be low mass. What about intermediate mass stars? Do they make S process elements? Well, there is evidence, but it's less compelling. So we have observations, and here I mean stars more massive than about 3 or 4 solar masses. These stars have what we call hot bottom burning, if you recall. This is where the base of the envelope gets hot enough to sustain proton capture nucleosynthesis. They can still have this dredge up process, mixing material from the helium shell, but now you've got a huge, really deep, big convective envelope. If I've got a 1.5 solar mass star, my envelope might only be, let's say, 0.6, 1.5 minus 0.6. So that's so it's not a huge envelope. Whereas if I have a 5 solar mass star, I might have a core of 1 solar mass, but I've got a 4 solar mass envelope. So the dilution of that helium shell material into that envelope is much greater. And so the chance of seeing enrichments at the surface go down. Okay, but there is evidence from observations that these intermediate bright Agb stars, because they're more massive, they're brighter, and they're often oxygen rich, evidence of hot bottom burning, and there is evidence they make S-process elements. In the Large Magellanic Clouds, Smith and Lambert and Wood from 1983 found evidence of enrichments of zirconium in the brightest Agb populations. Later, Hernandez in the Galaxy and also the Magellanic Clouds found evidence for rubidium enrichments in very bright, oxygen-rich, hot bottom burning stars. However, we aren't sure if the entire mass range of, say, 4 to 8 solar mass that can go through an Agb phase make these elements. How much they contribute to galactic chemical evolution is still probably a bit unsure, and there are still questions about how efficient this mixing is. Is it a stochastic process? Do all of our intermediate mass Agb stars go through this? There's still many open questions here. All right, let's just revise about Agb stars. Now, this is again a Kippenhahn diagram showing time on the x-axis versus mass. I'm really zooming in just on the region where we have stellar nucleosynthesis. So we've got the CO core. Above that, you've got a helium burning shell. Let's see if you can use my mouse here. You have helium burning ignited at the base of that shell. This leads to a convective thermal pulse that drives the star to expand. That leads to mixing, known as third dredger. So in this helium intershell, we make helium remains unburnt, so partial helium burning. We make carbon-12, maybe fluorine, but that's also where we make S-process elements. We have many of these dredge-up episodes that take some of those fresh metals, if you like, from the helium shell into the stellar envelope. And repeated mixing can increase the surface abundance, the surface carbon abundance, such that it's greater than oxygen. So we have a carbon star, and also consequently mixes up S-process elements. So then it's no surprise that we find carbon and S-process enrichment go together. So they're hand in hand with each other. What is the effect on mass from theoretical models? So in this plot, I'd like to show, and hopefully you can see from my little inset here. So this is showing proton number on the x-axis and X to iron on the y-axis. And these are the predictions from a number of theoretical models from about 1.2 solar mass, say, up to 5 solar mass. So the red points are my 1.15 stellar model. The 3 is shown in blue diamonds, and the black squares are the 5 solar mass prediction. This is for a metallicity that's maybe appropriate for the small Magellanic Cloud. So iron to hydrogen minus 0.7. So metal poor, but not super metal poor. Now, I want to focus on a couple of different things. Let's look at the peaks of the abundance predictions. If I look at my say 1.5 and so 1.15 and 3, you'll notice they have very similar distributions. We'll get to why later. And we also notice that they have peaks, that there's a peak at, say, strontium, there's a larger peak at barium, and then there's an even larger peak at lead. Now, recall that these correspond to magic numbers in neutrons, so lead 208, barium 138, and strontium 88. So these are where we have magic numbers, so there's no surprise there are peaks here. But in these models, you notice that the peak of barium is higher than strontium. Barium is what we call the heavy S compared to the light S at strontium. And then we have lead, which is higher again. And so what we see is that in low mass stars, such as the 1.15 and the 3, that these stars preferentially make the heaviest S-process elements. Why? These stars have higher, and we'll get to that, but these stars, even though they have lower, we'll see that they have lower neutron densities overall, but they release their neutron densities slowly. So their integrated neutron flux, which we call an exposure, is higher. So we can expose material to neutron captures for much longer, and this allows us to build up heavier elements. The 5 in comparison, there's a peak at rubidium, not strontium, so it's shifted, and this is because we're opening branching points. So we've opened a branching point to produce a peak at rubidium, but then there's not much barium and not much lead. This is because the neutron densities in these 5 solar mass, they're much higher to allow branching points to open, but the neutrons are around for only a short time. So you run out of neutrons super quickly, even though you have a lot of them. And that means you never actually get to the barium peak, let alone the lead peak. This is the main reason for these differences. Now, our low mass stars, neutrons are released in carbon-13 pockets. These are formed, and this is a very unknown process. There's still a lot of questions how this happens, but we think we mix a little bit of protons from the base of this convective envelope, which is hydrogen rich. We mix some protons into our convective helium shell. Those protons are captured by carbon-12, because there's a lot of carbon-12 here. That makes carbon-13. And over time, carbon-13 alpha N slowly releases neutrons to make oxygen-16. These neutrons are captured by iron to make heavy elements. And those heavy elements are then, when we have our next thermal pulse, they're mixed throughout this entire region, and then dredge up will mix then some of those S-process elements to the stellar surface. What about in our intermediate mass stars? Well, in our intermediate mass stars, we aren't even sure they have carbon-13 alpha N. However, they do, so the base of their helium intershells, though, they are hot enough to ignite neon-22 alpha N. Now, neon-22 alpha N is ignited at the base of the helium shell, produces neutrons. Those neutrons are captured by iron peak elements. And you make, and this helium convective, this convective helium shell then becomes enriched in S-process elements. These are very well mixed throughout this region very rapidly, and some of that's dredged to the stellar surface. So we end up having 2 different neutron sources for our stellar mass ranges. Low mass Agb stars mostly produce neutrons through the carbon-13 alpha N. This takes place during the radiative intershell region or time of the star's Agb life. The maximum neutron density is on the order of 10 to the 8 neutrons per cubic centimetre. Neutrons are released slowly, so over a really long time, maybe 10,000 years. So that means my neutron exposure, which is the integral of my essentially neutron density over time, is quite high at 0.3 per millibarn. My intermediate mass stars over, say, 4 solar mass, their intershell, we don't know if they have carbon-13 alpha N. There's not a lot of evidence for this, either way, actually. But we know their helium shells become hot enough to sustain neon-22 alpha N. Here, the maximum neutron density is much higher, maybe 10 to the 13 neutrons per cubic centimetre, up to that. But neutrons are only released for maybe 10 years at most, probably less, more like a few years. So that means the neutron exposure, my integrated neutrons, so the time over which I have neutrons, if I integrate that, it's much, much lower. It's only 0.02 per millibarn, and this is for solar metallicity. So this just shows what I mean here. The neutron density, this defines the details of the S-process path, where the density for neon-22 is much larger than for carbon-13. However, the neutron exposure tau defines the details of the overall distribution. And this is much higher for carbon-13 alpha N than neon-22, because this tau is the integral of the neutron density times thermal velocity over time. So that means if I integrate this, I've got 10 to the 4 years. So I've got neutrons released at 10 to the 8 neutrons per cubic centimetre over 10,000 years, compared to, say, 10 to the 13 over 10 years. So the overall exposure is much, much lower. And this means that the distributions are very, very different. What about the effect of metallicity? Now here I'm showing predictions of, they're all from a 2.5 solar metallicity star. The solar metallicity in black, these are the black points, for -1.4, so more than 10 times iron deficient compared to the sun, in red, and very low metallicity, so more than 100, so about 200 times the iron deficiency of the sun in blue. Now, you notice that the peaks here, now we see that, for example, the solar distribution, we make more barium than strontium, but we make more barium than lead. By the time you get to the most metal poor example here, our minus 2.3, so 200 times iron deficient compared to the sun. This theoretical prediction makes much more lead than barium and much more barium than strontium. So what causes this distribution? Again, it comes down to that tau relation I showed you before. Let's explain why. Now, carbon-13, again, here we're assuming that all neutrons are produced by carbon-13 alpha N. So we're not worrying about neon-22 here. Carbon-13 nuclei result in neutrons being produced by carbon-13 alpha N, and the main neutron absorber of these neutrons is iron-56. That means the neutron density is approximately equal to the number of carbon-13 nuclei divided by the number of iron-56. So you see that if you have many fewer iron nuclei, that you have a higher neutron density. Carbon-13 in the pocket is produced by proton captures on primary carbon-12, where carbon-12 itself is made as a primary process from the triple alpha. This means that carbon-13 is a primary neutron source. So what do those words mean? They just mean that the amount of carbon-13 I'm making in a solar metallicity star is the same as I'm making in a low metallicity star. So I'm always making the same amount of carbon-13 to first order, regardless of the metallicity. So it doesn't matter how much iron I have, but the amount of iron I have will greatly scale with the metallicity. So this means that the neutron density scales with the inverse of iron-56, i.e. with metallicity. That means that low metallicity stars produce more neutrons and therefore more heavy elements. This means that if I look at, for example, barium to strontium, that should increase with decreasing metallicity. We can actually test this using instead cerium to yttrium, which is the analog and more easily measurable. Is this true? Let's look at some observations of barium stars. This is from a recent paper by Che from 2018. So we have metallicity on the x-axis versus this is the ratio in square brackets of cerium to yttrium. All of these grey points down here, these are observations of barium stars. So barium stars, again, these are extrinsic stars. They receive their S process from a previous Agb companion. I've put some theoretical predictions from a few different groups here. Well, Che did this. So she took some of my results, some of the Fruity and new grid predictions, and they're all more or less consistent with each other. But the main result is that we see that both from theory and observations, that the cerium to yttrium abundance increases with decreasing metallicity as expected. This just means that we're making more heavy stuff, cerium, at the expense of lighter S process stuff like yttrium. And this is as a consequence of the amount, that's because that we have just as much carbon-13 at low metallicity, even though the amount of iron-56 that we start with is greatly decreases as I moved up to lower metallicity. I wanted to talk briefly about neutron density indicators. So rubidium is one. I mentioned that stars, intermediate mass stars, can make rubidium, and that's because of a branching point. There's actually two of them. This little chart down here shows that at krypton 85, we have a branching point. So we can, if you have lower neutron density, you bypass, so this gets bypassed, and the main path is shown as a solid line, and that gets to strontium 88. This is a magic number of neutrons. If you have higher neutron densities, you bypass the branching at krypton 85 and at rubidium 86, and you end up making rubidium 87, so which is also magic. And it turns out that depending on neutron density, you're much more likely, if you have high neutron density, such as what we find in an intermediate mass star, where neutrons are produced through neon-22 alpha N, we're much more likely to bypass to open these branching points and primarily make rubidium 87 at the expense of strontium 88. This means that if I can measure rubidium to strontium in stars, I can use this as an indicator of the neutron density. And indeed, this has been done. Most observations of low mass stars, so it's possible to measure both of these elements spectroscopically, and low mass stars do indeed have more strontium than rubidium, whereas some of the brightest, most massive Agb stars that enrich in S-process elements have much more rubidium than strontium, so which confirms that which confirms this theory. I want to finally, I guess, before I end and talk about the next, about some puzzles, I want to just mention S-process indicators. You might often see them in the literature, so it's just worth defining them. These are usually mentioned. We have LS, meaning light S-process elements, usually yttrium, strontium, zirconium. Sometimes you might see HS, heavy S-process elements, typically 2 to 4 elements around the barium peak, so barium, lanthanum, cerium. And then there's usually lead on its own. This is usually a measure of the weak S-process, LS, the main component, HS, and the strong component, again, lead. I've also put the zirconium, so rubidium to zirconium here. So zirconium is made along with strontium. So this is the same model mass, 3 solar mass models. These are theoretical predictions of different metallicity. So from metal rich, so this is a factor of about 2 above solar, down to almost 100, down to almost 100, almost 100 deficit of the solar ion to hydrogen ratio. Now, you can see that as this is the same 3 solar mass model, and if we look at the LS over HS, this increases initially. I must have some animation there that I haven't got rid of. So this goes down, so this goes up initially before going down. By the time I get to HS, you notice this only essentially goes up until I get to the lowest metallicity. Then you'll notice that HS to LS, that also turns over at about -0.7. But you notice that the lead peak only goes up. And that's because at the lowest metallicity, -1.8, that we're operating an S-processor closer to an equilibrium. So we're making essentially primarily mostly lead out of this star. And this is something that Roberto Galeno found in 1998 in his theoretical models. I've also highlighted rubidium to zirconium, and this is probably less about the S-process and more about the details of theoretical stellar evolution, where as you go to, if you take a model of the same mass, but you decrease the metallicity, the temperature in each burning zone becomes hotter. So low metallicity stars of the same mass are hotter than their more metal-rich counterparts. So this just means that my 3 solar mass of low metallicity is hot enough to ignite neon 22 alpha N, whereas it isn't at solar metallicity. So you notice that by the time I get to -1.8, I'm actually making more rubidium than I am zirconium in this particular model. So I've opened up my branching points and I've ignited neon 22 in the convective thermal pulses of the low metallicity 3 solar mass. All right, let's discuss some puzzles. I showed you this plot before. This is from an involved post-Agb star in the Magellanic Cloud. I highlighted how it's showing these huge enrichments of S-process elements. I did focus on a couple of issues. I'm not going to discuss the light element issues, but I will focus on the heavy element issues. You notice that the lead abundance, so there is a result here, it shows that blue line is a theoretical prediction from one of my models. You notice that it's actually a decent fit to almost all of those points except the lead. You see that the lead abundance that I predict is on the order of 3, so 1,000 times the solar ratio, compared to the star, which is about which is about 1.8, something like this. So it's orders of magnitude different. So is this a problem with the theoretical models, or is something else going on? And we wondered if there was quite a few discussions about this for a long time. We think something else is going on. Now, neutrons, I mentioned, form in carbon-13 pockets. We don't really understand how these form. Now, one way that people treat them, such as maybe Sergio Cristallo in his models, he has convective overshoot at the base of the convective envelope. And this basically is like here we treat convection as when you get to the border of a convective zone, we know the acceleration of the material that's in motion in the convective envelope is 0 there. but that doesn't mean its velocity is 0. So maybe it can overshoot a little bit and mix into the helium shell. So we think that's it likely happens. How deep it gets, we don't know. We have to treat this as a free parameter, which is how we can form carbon-13 pockets. Other people treat them in different ways. So there's a whole literature on this. In my review paper that I mentioned in my previous lecture, you can have a look at discussions about this point. But the summaries, we don't know how they form. There's a varying hypotheses put forward to form carbon-13 pockets. We also don't know how much hydrogen is needed to make a carbon-13 pocket. We know it can't be too much, otherwise you make nitrogen-14. Nitrogen-14 is what we call a poison for the S process. It sucks up all the neutrons, doesn't leave any for carbon-13. So we can't make too much. We also don't really know the effect of stellar rotation, although there are some newer papers now out this. So CEE has a recent paper where I think she considered in maybe her 2018 paper, maybe her more recent paper, she looked at the effect of stellar rotation. So the effect of stellar rotation on the S process is something we're starting to get a handle on. And the main summary is that it probably doesn't have a big effect on the Agb S process. Maybe by the time the stars get to the thermally pulsing Agb phase, the core has slowed down enough that stellar rotation or something else like magnetic fields, like Maurizio Busso discusses, maybe this has slowed down the rotation or it's counteracting its effects, and it doesn't essentially affect the S process too much. Anyway, lots of open questions still. Okay, what about the sudden mixing of protons? What if I mixed very rapidly, say under post-Agb conditions, where I've got a very thin convective envelope now, most of it's been eroded by mass loss. What if I mix in, I've got a convective helium shell, thermal helium instability, thermal pulse takes place when I have a very thin envelope mass. What if the energy from that thermal pulse mixes in some protons into a convective helium burning region very suddenly? What happens? It can lead to neutron densities on the order of 10 to the 15 neutrons per cubic centimeter. So you're producing neutrons at a much, much higher density than you do through traditional S process. This can lead to neutron captures under what we call I process or intermediate neutron capture like conditions. I've put the S process here. I've actually put 10 to the 13 for the S process, so less than this. So we think that the I process, this intermediate neutron capture process, can take place when you mix, anytime you mix protons into a convective helium burning region, such as a post-Agb star, or maybe a core helium flash. Are the lead abundances in post-Agb stars evidence of this? And what about, there are also some weird carbon-enhanced metal Pore stars, which we think are the result of an I process, such as discussed by Maria Lugaro's paper in 2012. Okay, so why do we think this? These are simulations of under I process conditions made by Melanie Hampel. She is a PhD student at Monash University, who's just finished. And we see some observed points for a post-Agb star compared to one of her I process simulations. And you know that, and we can see compared to, this black line up here is a typical S process. So we can see that her I process-like conditions, which operating not in equilibrium, so it's high neutron densities for a fairly short time, maybe a few days, and that produces something that looks like our post-Agb star. In fact, maybe that's what happened. You had protons ingested into a helium burning region, they burnt for a few days, that led to mixing, and we ended up with something that looks like this. There are also these carbon-enhanced metal Pore stars that show enrichments in both S and R process elements. These were a conundrum, a puzzle for a long time, but we think they are I process rich stars. This is again one of Melanie's, one of her nucleosynthesis predictions for the star. This is a bit of a poster child star, LP62544. So again, we have extra iron. This is her theoretical predictions in blue, and S process is shown in the dashed line. And we can see again that her model is able to match both the light S around strontium, the heavy S around lead, the europium abundance, which cannot be matched through an S process. as well as the lead abundance in this star. So where does the eye process occur in nature? We see perhaps observational evidence for it. What is the site of it? Where does it occur inside stars? Maybe low and intermediate mass stars of low metallicity that have proton ingestion. Maybe metal-free massive stars. There's been some work recently on accreting white dwarfs as a potential site of eye process elements in the galaxy. And this takes me to my final, essentially, component, which is about chemical evolution. So how will the eye process affect the early chemical evolution of the galaxy? From a work by Benoit Cote, he suggests it's important for the first peak, so yttrium, strontium, and zirconium, but anything else, don't know. Okay, this is my final part about the S process. This is looking at the chemical evolution of heavy elements. And by this, I mean, how do the elements build up in time inside galaxies? I'm not going to discuss chemical evolution more broadly. If you want a good background in this, I suggest having a look at, I'll give a reference to a paper by Chiaki Kobayashi from 2020. Her work is a good place to start, or the work by Beatrice Tinsley from the early 1980s or late 70s. Her work was the seminal work on galactic chemical evolution. So Tinsley would be the reference. Okay, so basically you make a chemical evolution model first that broadly matches observational features of the galaxy. What do I mean? Metallicity distribution function, etc. Next, we have to add yields of heavy elements. So these are a key ingredient, along with the regular things like star formation rate, initial mass functions, etc. So I add Agb yields, including S process elements. Massive star yields, including S process elements. Varying yields of R process, so merging neutron stars, anything from massive stars. There are many caveats here. This is still a work that, especially for the R process, but even for massive stars and S process, that's under significant development still. For example, the delayed time distribution of merging neutron stars is highly uncertain. We also know that massive star yields depend significantly on the numerical details of rotation. How you treat rotation in your stellar model has a big impact on the yields that you make. And it seems to depend from one code to another. Agb yields themselves depend on the treatment of the carbon-13 pocket and also mass loss. And we have huge uncertainties with both of those. We don't know how carbon-13 pockets are made still. So this leads to uncertainties. But we can make some progress, of course. These are Agb yields that I calculated. Here, this is for carbon, nitrogen, fluorine. I just have a few elements up to lead. And what do I mean by a yield? So this is a yield in solar masses as a function of initial mass. Let's let's just focus on this line or this plot first. So the yield is the amount of an isotope ejected into the ISM, interstellar medium, over the star's lifetime. This is the definition in maths, in mathematical language. So the yellow points show the yield. This is the raw yield. This is the amount ejected compared to the initial amount in the wind. So this is the showing in the blue squares here. Now the black dots are where I've weighted by a salpeter initial mass function, which is a power law. And you can see then, for example, if I look at barium, which is, maybe I'll focus in my next slide, which really focuses here. So this now is my yield of barium. I've just zoomed up. So I've got initial stellar mass versus the yield of barium in solar masses. The raw yield shown by my, again, blue squares. Now I've weighted by a salpeter initial mass function. So here we see that the intermediate mass range over 4 have been weighted out. That means that their contribution is less important simply because there's few of these stars in the galaxy. Okay, other people have made S process yields. The Monash group have a whole lot of yields that have been published, but there's also the Fruity database by Sergio Cristello. He's a lead on this, including a few models with rotation covering a large range in metallicity. The new grid models by Pignatari Ritter, and I think also Umberto Bettino. I should update this with some of Umberto's latest results. And very low metallicities, we have Garaili CS, Simon Campbell, Sarah Basterzo, and Monica Cruz, but there are no tabulated yield data sets available for low metallicities. And by that, I mean less than about minus 2.3. So there's still some things lacking. Generally, yields for very low metallicities for all stellar masses are lacking. So these yields are not available, or they're very sparse, maybe for 1 or 2 models, masses. And there's also no super Agb S process yields tabulated. And by that, I mean stars over about 8 solar mass. So, but what can we do with the yields we have? Well, we can make a galactic chemical evolution model, including heavy elements. So this is something that I did with Maria Lugaro and Chiaki Kobayashi, and we published this last year, and we included everything. So we tried to get theoretical yields for all elements up to uranium. And so we include all the R process sources we could find and all the S process sources we could find at the time. People have since published more S process yields for massive stars, and this has been reflected in work by Nikos Prantsos. And Cote has also done this for heavy elements as well. So here I'm highlighting some lovely strange elements: ytterbium, hafnium, iridium, lead, thorium, and uranium, of course. And you see we've put observational data points where we can find them. You see for some elements like iridium, there's very few. Thorium, there's few. There's some, though. Uranium, none. So these are the people. I'm on the left here. These are the people who made these heavy element predictions. I want to focus, this is almost my last slide. This is the history of strontium in the galaxy using our model. So we've got the S process prediction in dash. So this is again iron to hydrogen. So think of this as a proxy for time in a chemical evolution model. In these sorts of calculations we are making, they are 1-to-1. That means that time increases from the left up to the right. So we go from the early galaxy in -4 through to the present day galaxy. We have lots of observations for strontium. It's an element that's fairly easy to measure. And we have strontium to iron for these observational data points. Then we have our S plus R contribution. A few key things. This model matches the composition of strontium with the yields we have. We don't need any other sources. No, sometimes there's this light element primary process, don't need it. We don't need an I process. But maybe it could be important at low metallicities where you notice there is some considerable spread. So this is really a summary. The origin of heavy elements, our process makes about half. Maybe there's a couple of sites. Agb stars make about half, and there's a couple of sites. I process, it occurs in nature, but how much does it contribute to the chemical evolution of heavy elements? Don't know yet. Questions? This leads me to my very final summary for both lectures. I focused first on the Agb stars. This is the last complex phase of stellar evolution for low and intermediate mass stars. This brief phase leads to complex nucleosynthesis, which depends both on the initial stellar mass and initial stellar metallicity. The main result, Agb stars make carbon, nitrogen, fluorine, and they are a main source of heavy elements in the galaxy. The S process is one pathway involving neutron captures to make roughly half of all elements heavier than iron. The main site of the S process is Agb stars. However, the details depend on neutron density, on neutron production, and ultimately, therefore, neutron density. There is observational evidence for an intermediate neutron capture process in nature. What is the site, though? Is it mostly accreting white dwarfs? Can it occur in Agb stars, post-Agb stars, metal-free massive stars? I think I'd like to leave you with the idea that we've made considerable progress and we can now do quantitative galactic chemical evolution studies of heavy elements, but there's still many open questions for you to solve.